As you will have discovered, polynomial equations are simply equations that have the same term raised to a number of different and positive powers. Although there are higher order polynomial equations, those of most use to us are quadratic equations, which contain a constant term, a linear term, and a squared term. Quadratic equations occur frequently throughout mathematics, and it is useful that we have a number of ways of solving them. And by solving them, I mean techniques for finding the roots of the equation. That just means finding those values for which the result of the equation is zero. In this lecture, we'll consider some of the most useful methods. Firstly, by factorising the equation. Secondly, by using the familiar general solution to a quadratic equation. And thirdly, using what is probably a new method to you, a method known as completing the square. Factorisation is really only useful when dealing with very simple equations such as in this example. X squared plus 2x minus 8 is equal to 0. And by factorising, I mean rewriting the equation in another form which is easy to solve. In this case, we will require an equation such that it has the form x plus a multiplied by x plus b is equal to 0. There is only one x squared term, so the first part of each term must be just x times x. The a and b coefficients can be found by considering that their product, i.e. a times b, must equal minus 8, and their sum, a plus b, must equal plus 2. The way I do this is to consider the factors of 8, which are 1, 2, 4, and 8 itself. I want two factors that when multiplied together give me minus 8. Now this could be achieved by either 1 times 8 with either 1 or 8 being negative, or 2 times 4, again with either 2 or 4 being negative. But I also need their sum to be plus 2. And the only way that this can be achieved is with plus 4 and minus 2. Plus 4 times minus 2 is minus 8, and plus 4 plus minus 2 is plus 2 as required. So we have now factorised the original equation into the equation x plus 4 multiplied by x minus 2 is equal to 0. This is two linear solutions. Either x plus 4 is equal to 0, in which case x equals minus 4, or x minus 2 is equal to 0, in which case x is equal to 2. Consider now a slightly more awkward example. 3x squared minus 13x minus 10 is equal to 0. Here we can see that there are 3x squared, so the solution must have the form 3x plus a multiplied by x plus b is equal to 0. This means that we now want a times b to be equal to minus 10 and a plus 3b to equal minus 13. The numbers we need to achieve this are a bit more difficult to see this time, and the best way of finding the correct ones is again to consider the factors of 10 and then use trial and error to find which combination gives us the correct values. Although 1 and 10 are factors of 10, they don't give us the right solution, so the correct factors must be 2 and 5, which gives us 3x plus 2 multiplied by x minus 5 equal to 0 as the factorised equation. Now that we have factorised the equation, the two linear terms are easy to solve. If 3x plus 2 is equal to 0, then x is equal to minus 2/3, and if x minus 5 is equal to 0, x must equal 5. If it gets any more complicated than this, then the easiest way to solve the equation is to use the formula. The formula solution works in every case for solving a quadratic, but can sometimes lead to more work than is necessary. If the solutions are obvious and the equation can be factorised easily, then do it. It saves a lot of work. To use the formula, we must first write the equation in standard form, i.e. ax squared plus bx plus c is equal to 0. Then extract the a, b and c coefficients, remembering to include the sign of the term 2, and just plug the numbers into the general solution. Simplify, and hey presto, there are the answers. So let's try an example. X squared minus 2x minus 1 is equal to 0. The A coefficient is plus 8, the B coefficient is minus 2, and the C coefficient is minus 1. Plugging these into the general solution gives x is equal to minus 2 plus or minus the square root of minus 2 squared minus 4 times 8 times minus 1 all over 2 times 8. Now this simplifies to 2 plus or minus the square root of 36, which is of course 6, and then dividing the results by 16. This gives us the two solutions. X is equal to 8 over 16, or 1/2, or x is equal to minus 4 over 16, which is minus 1/4. In the previous example, the term b squared minus 4ac gave us a simple square root of 6, and the solution became very much easier. In fact, the formula solution gives us a very simple test to see whether or not simple factors, i.e. integers, occur in the factorised form of the equation. In other words, whether or not we could use the simple factorisation method to solve the equation. As we know, all quadratic equations can be written in a standard form. Once we have the equation in a standard form, we need to evaluate the term b squared minus 4ac. If the result is a squared integer, then the solution will have simple factors. If not, then it does not have a simple factorisation. So using the previous example, 8x squared minus 2x minus 1, we've already seen that b squared minus 4ac was 6 squared, so it will have a simple factorisation. In fact, it can be factored to become 4x plus 1 multiplied by 2x minus 1. Simple integers squared like this are known as perfect squares. So 9, 16, 25, 36, etc. are all perfect squares. We can extend this idea of using perfect squares to solve any quadratic equation, but let's first try an example. X squared minus 6x minus 4 is equal to 0. Checking, b squared minus 4ac gives 52, which isn't a perfect square, so we already know that it will not have simple factors. So let's rearrange the equation slightly by adding 4 to each side. Then we can add half the b coefficient squared to both sides. I'll explain why in a moment, but for now let's just do it. That gives us x squared minus 6x plus minus 3 squared on the left hand side and 4 plus minus 3 squared on the right. Multiplying out the brackets gives x squared minus 6x plus 9 is equal to 13. The left hand side factors very easily now into x minus 3 squared. Taking the square roots of both sides of the equation gives us x minus 3 equals the square root of 13, which can be very easily solved to give x equal to about 3.6056 or minus 0.606. I think you'll agree that that was really quite remarkably easy to do. What we did was add a number to both sides of the equation so that the left hand side could be factored very easily into a simple squared term. In other words, the number that we need to add to complete the square, which is why this method is called completing the square. The trick, if it can be called that, was in finding what number to add to both sides. It turns out that add half the b coefficient squared is always the number we need to add. Let's try another example. X squared plus 8x plus 5 is equal to 0. This method of completing the square works for all quadratics, but it's worth checking to see whether or not we could just factorise it simply first. In this case, b squared minus 4ac is equal to 44, so no, it won't have simple factors. So we rearrange the equation so that the constant term, i.e. the c coefficient, is on the right hand side, giving us x squared plus 8x is equal to minus 5. Add half the b coefficient squared to both sides, 4 squared in this case, to give x squared plus 8x plus 16 is equal to 11. The left hand side factors nicely to become x plus 4 squared. Take the square root of both sides and solve to give x is equal to about minus 0.683 or x is equal to minus 7.317. The only complication with this method arises when the a coefficient is not unity, or in other words 1. In those cases, all we need to do is to divide through by the a coefficient first and then carry on as before. So taking another example this time, 4x squared minus 16x plus 3 is equal to 0. Since the a coefficient is not 1, divide everything by the a coefficient of 4 to give x squared minus 4x plus 3/4 is equal to 0. Rearrange as before to give x squared minus 4x is equal to minus 0.75 and add half the b coefficient squared, minus 2 squared in this example. Factorise the left hand side, which gives us x minus 2 squared. Take the square root of both sides and solve to give x is equal to 0.197 or x is equal to 3.803. So let's summarise this method of completing the square. In summary, the first stage is to divide through by the a coefficient if it isn't actually 1. Second, we rearrange to put the constant term on the right hand side. Third, we add half the new b coefficient squared to both sides of the equation. 4, we factorise the left hand side. 5, we take the square roots of both sides of the equation. And 6, we solve it for x. This method will work for any quadratic equation. We could then apply it to the standard form of a quadratic equation, i.e. ax squared plus bx plus c is equal to 0. If we were to do that, then surprise, surprise, we end up with the general solution to a quadratic equation. I'm not going to show it here, but you could try this yourself to see how it can be done. This is the end of the Solving Quadratics lecture. Thank you for watching.